This conference will now be recorded.
All right, good morning. My name is Greg Wadley with CTC and Associates, and I'm the Clear Roads Administrator. We're here for the final project webinar for the project entitled Standard Test Procedures for Ice Melting Capacity of De-icers. This research effort is led by Xiaoming Shi of Washington State University. Before we turn it over to Xiaoming, I want to let everybody know that this webinar is being recorded and will be posted on the Clear Roads website later this week for viewing by you and your colleagues at your convenience. We also ask that unless you're speaking, please remain off camera and keep your microphone on mute. However, if you have any questions or comments, please do enter those into the chat box and we'll address them at the end of the presentation. So I think that's really all I needed to say. So I'm going to turn it over to Xiaoming. And Xiaoming, whenever you're ready.
Thank you, Greg. Thank you, everyone. And yes, this is the Clear Roads project final presentation. The title is Standardized Test Procedures for Ice Melting Capacity of De-icers. And the research team included myself, Dr. Mahdi, Anwar Nazari, and a few other undergrad students, and also Mr. Paul Braun and Mr. Dave Bergner. Actually, today, Dr. Nazari will present on behalf of our team. So Mahdi, the floor is yours.
Thanks. So let me start. In this project, the objective the objective was to evaluate the suitability of mechanical rocker test as a standardized laboratory test that can realistically and robustly assess the performance of the ISO data-driven purchasing decisions. So as you know, there is another test which is very common in the market, which is SHRP. So first, we want to compare the mechanical rocker test as a new method to SHRP to see what are the advantages and disadvantages of this method. In the first, in mechanical rocker test, we are measuring ice mass, but in SHRP, we are measuring the brine volume. So, when in SHRP method, I have done for two of my research articles. We make a flat layer of ice and put the icers on top of that and wait until it melts and measure the volume of the brine in different times. So in this method, for instance, we should take out the sample from the freezer and measure the volume of the brine, that it can make some error in the results. But in mechanical rocker test, when you put the de-icer inside the thermos, you start the test and finally just you measure the volume. So it can be one reason that mechanical rocker has advantages compared to SHRP method. And also, in reality, we don't have just one layer of ice. We have ice particles and also snow. So I think the mechanical rocker test can better simulate the real conditions than SHRP in terms of the form of the ice. Also, another point is mechanical mixing. In the road, we have vehicles and they have tires, so they continuously mix de-icer, snow, and ice. So we have some kind of mechanical mixing in real world. But in SHRP test, we don't. It is some kind of a static method. We just put the de-icer on top of the ice and wait until it melts. But in mechanical rocker test, some kind of dynamic test, we have mixing of continuously mixing of the ice and de-icers. So this some kind of friction and mechanical action can also has a significant effect on the results of the ice melting test. And another point, actually, some kind of I mentioned, we have multiple ice cubes, and in the mechanical rocker test, more than 30, actually 33 ice cubes in a mechanical rocker test. But in the SHRP, we have just a single layer of flat ice. So as I said, having multiple ice cubes can be better in terms of simulating the real conditions. And also testing temperature in SHRP method, the test temperature is not accordance to many freezers. So but in a mechanical rocker test, we can do the test at 15 and 0 Fahrenheit. So many chest freezers can afford to do the test at these temperatures. So as a result, we can use cheaper equipment for mechanical rocker test. And also in mechanical rocker test, some kind of measuring the ice melting capacity compared to SHRP, that we measure ice melting rate, actually. So for instance, in SHRP method, we have ice. We put the ice on top of that, and as measured, as I told you, by using a syringe, we measure ice melting rate. So we collect the brine, actually. And there can be some kind of error when you collect the brine, because I have done this by myself. But in ice melting capacity, we measure the weight of the ice cubes. So as a result, it can be more precise. So we measure the weight of ice cube before the test and after the test, so we can see how much of the ice has been melted. So for doing mechanical rocker test, first we need styrofoam cups, 10 styrofoam cups. 5 of them we name them as A, B, C, D, E, and the other 5 A, B, B, C, C, D, D, and E. So cups A, B, C, D, and E will be used for measurement of the mass of ice before testing, and the other cups will be used to measure the mass of melted ice after rocking. So actually, we measure the weight of the ice before and after the test, then we can calculate how much of the ice is melted. And to do the test, we need a thermos. It can be any brand. Actually, we don't want to advertise a special brand, but the thermos brand was used in this research. And you can see here, this is an ice tray. The capacity of each mold should be 1.3 milliliter. So we put 1.3 milliliter of DI water into each of these molds, and we make actually 33 ice cubes. After that, we put 30 milliliter of liquid chemical deicer into each of the 5 thermoses labeled as A to E. And Then we place the thermoses and the ice cube trays into the freezer. After that, we measured the mass of cup A and 33 ice cubes. It is before the test. Then we place them in the freezer again and remove the thermos A and pour the ice cubes into it. And then after closing it, we put it in the mechanical rocker and let it for 15 minutes to rock. And at the end of 15 minutes, we remove the lid of the thermos and pour the contents in the number 4 seat. And here you can see an example. And also we place the cup AA, which was for collecting the ice after the experiment, near to the sieve and try to put the ices inside it. And the next step is we measure the weight of the cup and the ice cubes after the test. So we repeat this procedure for 5 times, and then we use this equation to measure the ice melting capacity. So it is the mass of ice melted, which is the difference between the mass of ice before the experiment and after the experiment, and the volume of the de-icer. We use 30 milliliter of de-icer. As a result, the unit of this test is gram per milliliter. The next step is I want to talk about the constant involved in this test method. The first one is the total volume of the ice per thermos. Actually, we used in all of the cases except one case, we used 33 ice cubes, each of them with a capacity of 1.3 milliliter. As a result, the total volume of our ice cubes was about 43 or 42.9 milliliter. So, and in just one case, I will talk about it later, we tried to also see the effect of the mold size. We used the mold with less capacity. So the capacity of the volume of each ice cube was 1.85 milliliter. So to keep the total volume of the ice cubes constant, we used 55 ice cube at there. So as a result, the total volume of ice per thermos was constant in this research. And the next one is the number of cups and thermoses. So 5 thermoses and 10 cups per sample. Also, the third one is the volume of the liquid de-icer in each thermos, which is 30 milliliter. And for 5 thermoses, we need 150 milliliter of liquid de-icer. And test temperature, actually we used 2 test temperature, 0 Fahrenheit and 15. So 0 Fahrenheit or minus 17.8 Celsius used for 29% magnesium chloride, 32% calcium chloride, and products A, D, E, and G. Or also you can use it for acetate-based products. And 15 Fahrenheit or minus 9.4 Celsius used for 23% sodium chloride and products B, C, and F, or in general sodium chloride based products. So the variables involved in this test method was tilt angle. We use 2 tilt angles, 8 and 10 degrees. Also, the frequency was 70 and 90 RPM. The time was 12 and 15 minutes. Ice cube tray capacity was 0.85 milliliter, as I mentioned before, and 1.3 milliliter. Most of the tests have been done using this one, and 2.4 milliliter. So in case of 2.4 milliliter, we did not fill the mold with 2.4 milliliter. We just used 1.3 milliliter. We wanted to see the effect of the shape of the ice. I will talk about it later. And the shape of the thermos, we used two different shapes, but both of them were cylindrical, but with different sizes and different diameter and different height. So one of them 3.7 inches wide and 5.5 inches height, and the other one 3 inches wide and 9.7 inches high. So we wanted to see if the change in the size of the thermos can significantly affect the results or not. And the chemicals involved in test, also we use different chemicals. We used solid deicers and made them into brine by combining them with the DI water. For this purpose, we use sodium chloride, mag chloride, and calcium chloride to make 23% sodium chloride solution, 29% magnesium chloride solution, and 32% calcium chloride solution. And also there were some liquid commercial deicers. We named them as A to G. So to evaluate the test protocol by ASTM standards, we used first precision. In this regard, we have two kind of precision. One is single operator precision, which is repeatability, and the other one is multi-laboratory precision, which is reproducibility. And also we use the ruggedness to evaluate significant effects. So those variable parameters that I mentioned before, we tested them to see if they have significant effect on the ice melting capacity of the deicers or not. So I give you some equations here about the precision according to ASTM E691. To calculate the precision, let's say we have measured the ice melting capacity of the icers. If we can consider ice melting capacity here as X. So we calculate the average of the test results in one cell. In one cell here, it means, for instance, one group has measured ice melting capacity for deicer A. So we make an average from the results, and then using equation 2, we can calculate a standard deviation, which is S here. Then also we have another factor which is mentioned in equation 3. We calculate the average of the cell averages for one material. So here we consider different groups, and for one deicer, we can average of the cell average of the ice melting capacity obtained by each group. Then using equation 4, we can calculate cell deviation by subtracting the average test results in one cell by average of cell averages for one material. And then in equation 5, we use equation 5 to calculate a standard deviation of cell averages. And equation 6 shows another parameter, which is S sub R, This one is the repeatability standard deviation. Then we can calculate S sub L, which is between laboratory standard deviation using equations 7 and 8. And using equation 9, we can calculate S sub capital R, which is a reproducibility standard deviation. And finally, using equations 12 and 13, we can calculate the 95% repeatability and reproducibility limits, which are shown with small and capital R. So here, these are the results for ice melting capacity of 23% sodium chloride solutions. We named the group as L1 to L7. Actually, 7 laboratories participated in this report, in this research, and WSU had 2 teams. In total, we had 8 teams. But we use some filtering of the data. I will explain about them later. After filtering, we separated, for instance, for the case of sodium chloride solution, 7 groups, and put the data here. So you can see ice melting capacity of the 23% sodium chloride is presented in the second column. Then standard deviation in the third column. Then we have calculated the S sub R and S sub capital R, and after that, at this column, which is shown with the orange box, we have acceptable repeatability, which is mentioned here as equal to 2.8 times S sub R. So you can see here all of the standard deviation values for ice melting capacity are less than this number, which is 0.031, which shows that the precision of the test was good for this case. And also another one, last column is acceptable reproducibility, which is also showed in the last line, which is acceptable reproducibility, which is equal to 2.8 times S sub capital R, which is here S sub capital R. So the value is 0.208. Also, again, all of the standard deviation are less than this parameter, which is good and shows that in terms of precision, we have passed this step for measuring ice melting capacity of 23% sodium chloride solution. Then, yeah, here I have shown another the results for other de-icers. 32% calcium chloride, again, a standard deviation here in this column, and acceptable repeatability and reproducibility. So all of the standard deviation values are less than these 2 parameters. Again, we have for 29% magnesium chloride, the same story. The precision is acceptable. Then we have for de-icer A and de-icer B, de-icer C, de-icer D, and de-icer E, and de-icer F, and finally de-icer G. Yeah, you can see the maximum number, for instance, in case of de-icer G, the maximum standard deviation in the last line is 0.035, which is less than acceptable repeatability, which is 0.039. So and it is also less than acceptable reproducibility, which is 0.179. So then the next step, we wanted to see which changing which parameter has significant effect on the ice melting capacity of the de-icers. For this step, we used standard ASTM C1067. So to do this, the method of analysis, which is known as analysis of variance, or ANOVA, is used. So the error variance is based on the scatter of the replicate determinations about their average, set average, and actually for the last three parameters we used average. For the other first four parameters we used the single individual data. So we studied the effect of rotational speed, effect of tilt angle, effect of testing duration, effect of operating laboratory, and the effect of thermos shape, effect of ice cube shape, and effect of ice cube volume. So to study the effect of rotational speed, we use 70 RPM and 90 RPM. In general, we try to get some kind of about 20% change. So about 20% change, if we consider that, gives us 70 and 90 RPM. The original number is 90 RPM, so we decreased it by almost 20% to get 70% RPM. So here you can see, for instance, 23% sodium chloride solution, yeah, you can see visually that they are very close, the results. Also for the ices B, C, and F, but for the ices 29% magnesium chloride or de-icer air, those with more ice melting capacity, there is a little bit difference. So then we did ANOVA analysis. In general, the p-value of ANOVA analysis was 0.22 and something. So the first two numbers are two digits are important for us, because if p is more than 0.05, then the difference is not statistically significant. But if p is equal or less than 0.05, the difference is statistically significant. In this case, it is much more than 0.05, so it shows that the difference is not statistically significant. As a result, we can say about 20% change in the rotational speed doesn't have any significant effect on the ice melting capacity results. The next step, we changed the tilt angle. The original number is 10. We decreased it to 8. Also here again we can see same trend. The results are very close to each other, but in case of sodium chloride A, B, C, and F, they are closer. So again, we use ANOVA analysis to get the p-value. Here again, p-value is 0.27, and which is more than 0.07. As a result, changing the tilt angle from 10 to 8 doesn't have any significant effect on the results. In the next step, we studied the effect of testing duration. We changed the duration from 15 to 12 minutes. So Again, you can see the results are very close, especially in case of sodium chloride and BC and F deicers. But in total, if we analyze all of the data, again, the p-value is much higher than the 0.05. Then in the next step, we have the effect of operating laboratory. So 7 groups participated in this research, Washington State University with 2 teams, and Western Transportation Institute, Envirotech Services, Montana DOT, Nebraska DOT, Analytical Laboratories, and Paradigm Group. And here are the mechanical rocker model that they have used. All of them except WTI have used a thermoscientific model. So then here are the ice melting capacity of the different deicers, and different groups have been shown with different colors. I have mentioned here. So, and here, for instance, you see some of the results are missed because we filtered the data, and I will explain it later how we did it. So then here in this slide, I have shown this process. We have raw data. Then we use a coefficient of variance of 10% to filter the data. Those with coefficient of those ice melting capacities which have coefficient of variance more than 10% within each group. So, for instance, one group has measured ice melting capacity for deicer A, and the results coefficient variance of the result is more than 10%. So we remove that group for this analysis. And then next step, we use outliers, removed outliers based on ASTM C802. This is qualification control step 1. Then qualification control step 2. This one, step 2, was some kind of innovative. We made in our group actually this this standard. So we because you know, the deicers A to G are commercial deicers, so there is no standard to compare those deicer with. But analytical grade deicers, there are a lot of this research about them, and because their composition is known, so as a result, you can the results are repeatable for analytical grade deicers. Everybody can purchase sodium chloride and make 23% sodium chloride solution. So as a result, we used 2 deicers, sodium chloride solution and magnesium chloride, to filter the data. So sodium chloride solution, also we used 2 temperature, test temperature, 15 Fahrenheit and 0 Fahrenheit. We reached these temperatures after some trial and error. So for 15 Fahrenheit, we use sodium chloride, 23% sodium chloride solution as a standard. And for 0 Fahrenheit, we use 29% magnesium chloride as a standard. Then we calculated the median minus plus 2 times standard deviation of ice melting capacities of these 2 deicers obtained by the groups, and we remove the groups with control that have ice melting capacities out of this range. So, for instance, for 15 Fahrenheit, the results obtained in 15 Fahrenheit, we finally came up with group L1, L4. It means that we have removed L2 and L3. And we have also L5, L6, L7, and also we excluded deicer B for L7. And for 0 Fahrenheit, we have group L1, L2, L4, L6, and L7. So here is ANOVA analysis of ice melting capacities tested at 15 Fahrenheit by group L1, L4, L5, L6, and L7. So you can see the p-value is 0.056 something. This is more than 0.05. So as a result, we consider, because if we round it, it gives us 0.06. So the difference is not considered statistically significant. But for 0 Fahrenheit, the results obtained for 0 Fahrenheit, the p-value is very low, much less than 0.05. So it shows that the difference is statistically significant. So here we can see that the test temperature has significant effect on the results. So in the next step, we wanted to see the source of this error. So okay, sorry. Then we also measured the previous slide. We used the as you can see here, we use individual data, but in the next slide, we use average data. So to do ANOVA analysis, if we use average data, the p-value for 15 Fahrenheit, again, it is much higher than this limit. But for the case of 0 Fahrenheit, it is close, but higher than 0.05, which is showing if we use average data, the difference is not statistically significant, but it is still much less than the case of 15 Fahrenheit. So in the next step, because we have used two kind of deicers, commercial deicers and analytical deicers. We suspected that the difference can come from commercial deicers. So we did ANOVA analysis for commercial deicers at 15 Fahrenheit and 0 Fahrenheit. At 15 Fahrenheit, the difference again is not significant, but at 0 Fahrenheit, you can see the value is too low. So so we can see that commercial deicer, actually the difference between ice melting capacities are significant. So then even you can see here even we use mean average ice melting capacities. Even we use average ice melting capacities, we have a significant difference. So as a result, for the next step in ruggedness test, we did not test all of the deicers. We just tested two commercial deicers for 0 Fahrenheit and two commercial deicers for 15 Fahrenheit. So um, actually to decrease the number of experiments that we want to do. So here we have the results of ice melting capacity for deicers A, B, C, D, and we have used short and tall thermos for this experiment. Here are the pictures of these two thermos, and we can see the p-value for the ice melting capacities is much higher than the threshold 0.57, which shows that changing the shape of the thermos without changing the capacity, or both of them have same capacity, I think 16 ohm. So if we just change the shape of the thermos, it doesn't have a significant effect on the ice melting capacities. Another factor is ice cube shape. So maybe without maybe not everybody can find the ice tray with a capacity of 1.3 ml for each mold. So what about the case that somebody has an ice cube tray with bigger molds size? So for this purpose, we made two kind of ice cube shapes, cuboid and cube. And here are the ice melting capacities results for deicer A to D. And again, you can see the ANOVA analysis results shows that the p-value is not significant. Here are the shapes of the ice melting trays that we have used. In the left, we have ice melting capacity trays with capacity of 1.3 milliliter for each mold, and here we have ice melting capacities tray with bigger molds, but we did not fill these molds completely. We just used the capacity of each mold in this tray is 2.4 milliliter, but we just filled it with 1.3 milliliter. As a result, the shape of the cube is not the shape of the ice is not cube. It is a cuboid shape, but we can see again it doesn't have significant effect on the ice melting capacity of the deicers. So the other parameter was ice cube volume. What if we use, for instance, ice trays with lower capacity for each mold? In this case, we used 0.85 milliliter. But as I mentioned before, when we use these molds, we try to keep the total volume of ice constant. Because of that, we use more ice cubes. So ice melting capacities are presented here for, again, the deicers A to D. And the p-value, it is not significant again. And here are the shapes of these ice trays. The white ice tray is associated with 0.85 milliliter capacity for each mold, and the blue one for 1.3 milliliter capacity. As I mentioned before, you can see the total volume of ice is about 42 milliliter. So we used 50 actually ice cubes to get similar volume. And so at the end, I give you some concluding remarks about this research. The test protocol performed well in both precision and ruggedness. Changes in average ice melting capacity value due to different rotational speeds, tilt angles, test durations, and operating laboratory are not statistically significant. And also, ruggedness tests showed that the average ice melting capacity values do not change significantly due to the change in the shape of the thermos ice cube, shape of the ice cube, and the volume of the ice cube. And we saw that the operating laboratory is the most sensitive variable in this research. Also, ice melting capacity value of commercial de-icers is more sensitive to test temperature than that of analytical grade de-icers. So then to minimize the interlaboratory variability, we incorporated two data acceptance checks. First was coefficient of variance, or COV. The coefficient of variance of ice melting capacity for each lab should not be more than 6%. But we accepted the COVs up to 10% for analysis. Otherwise, we should remove many laboratories from the research. Yeah. All the measurements were done in 5 replicas. And also, we used two certified reference values of ice melting capacity. First was for 23% sodium chloride solution at testing temperature of 15 Fahrenheit. The value was 0.146 and minus plus 0.094 gram per milliliter. And we use a standard value for 29% magnesium chloride solution and testing the temperature of 0 Fahrenheit, which is 0.384 minus plus 0.098 gram per milliliter. So thank you for your attention. Please let me know if you have any questions.
All right, thank you, Mehdi. Xiaoming, do you have any remarks to wrap this up?
Sure. Mehdi, if you could go to the summary slide, one comment, or actually the quality control slide, sorry. I want to add one clarification. The Q1, Q2, yeah, that one. Yes, could you, yeah. So one clarification here is the level 1 quality control really is looking at how reproducible the results are from the same group for the same de-icer. So, but sometimes they pass that quality control check, but when you compare them against everybody else, they're way off. That, in other words, there's a bias. Maybe their, freezer temperature sensor is off by, 2 degrees or something like that. So that's why there's a need to insert this reference chemical so that we know they're not drifting away from the norm. So that's the level 2 quality control. That's the only comment I want to make. Thank you. Oh, and also maybe Greg, you want to mention where things are with the AASHTO.
Yep, I planned on just making a very quick remark that that this test was recently provisionally approved by AASHTO and will be a part of. They're going to publish it this summer. So this is the first test method that's through ClearRoads that's been approved by AASHTO, and we are very proud of that. really appreciate the work of Sean Ming and his research team, and also all the hard work put together put forth by our project subcommittee, which do I have that in front of me right now? I do. Let me scroll up here really quick and just thank them, because this is a this was a year 18 project, in case you guys hadn't noticed, and it wasn't just the test method that that really kind of caused it to take that long, but it was mainly, a lot of it had to do with the AASHTO approval process, and so and keeping the research team on to help us respond to comments from AASHTO members, and kind of going back and forth in like 9 different iterations at least of the test method itself. So it was a lot of work, and so I want to thank Jasmine Donlinger from Nebraska, who's a Clear Roads chemist, Jeff Pfeiffer from West Virginia, Doug McBroom, Montana, Patty Caswell, Oregon, James Moore in Washington, Tom Peters, Minnesota, and then also Rick Nelson from AASHTO, and also Dave Hansen from Nebraska that helped out Jasmine as well. So, and if there's anybody else I didn't mention, oh yeah, yep, thank you, Jasmine. Ty Barger was the Clear Roads member when this project for Nebraska, when this project was brought forward, and so he was the one that that was the project champion in the beginning of this project. But Jasmine has since taken over his role after he left the agency. So Rick says, thanks and kudos to Mike and Jasmine and their Talking Winter Ops episode 96, Shake and Not Stir, the rocker ice melting test method. So over 125 downloads so far. So yes, please visit the Talking Winter Ops website, because you will get another enough further insight into this project from that podcast. Jasmine, do you have anything else that you want to add to this, or anybody else from that project subcommittee?
Thanks, Greg. Yeah, no, I think I'm good. Thank you for mentioning Ty. That was really kind of the only thing I really wanted to make sure that he got some credit for this as well. But thank you, Sean Ming, you and your team, all the hard work. And I know that we kind of asked a lot of you there at points, but really appreciate all that hard work. Thank you.
Well, it's a great pleasure to work with you and the entire team. And I also want to thank the participating laboratories, especially during the pandemic. It was kind of challenging to get supplies or manpower to run some of these tests, and back and forth. I think we run the second time of a round robin test to get things right. And yeah, this is the list, and thanks to every one of them. It's just a team effort.
Yeah, absolutely great point, Sean Ming. Thank you. All right, well, thank you so much for everybody's time today. Again, I will have this recording posted on the project page later this week. So, the final report will be posted on the project page eventually, as well as a research summary. And like I said, the podcast on AASHTO's Talking Winter Ops page, if you want to get further insight into this project. And when it does, when the test method does get published this summer through AASHTO, I will probably provide a link to that from the project page and alert the rest of the Clear Roads group to that when it happens. Okay, thank you, everybody. Have a great rest of your day.
Thank you, everyone.
Thanks all.
Thank you.